I'm Roy Eriksson. Thank you for joining us. Today's webinar will be an overview and demonstration of Eriksson Wall, our new generation software for the design of solid or insulated precast structural wall panels. We'll begin the presentation with an overview of your options for starting a job. Then we'll walk through the different areas of the program and program inputs and output options. This will be followed with a demonstration of the process of starting a new job, working with the program, and taking it through to final results. During this live webinar, our staff will be standing by ready to answer your questions. Please submit them online through the GoToWebinar interface anytime throughout the presentation. Conducting this webinar will be Justin Callahan, the project manager and one of the lead programmer engineers on the project. We hope you enjoy the webinar.
Thank you, Roy. So I'm just going to jump right into this. So what I'm going to do is I'm going to go through an overview of the interface and then kind of explain some of our design philosophy, some things that we really focus for when putting this program together. And then we're going to work through a design example. So what I'm going to do is I'm going to take this basic panel and I'm going to build an insulated wall panel from scratch with you, kind of showing you how to flow through the program. So the first screen that you open up to is the startup screen. The startup screen really has three areas. It has a list of your most recently used files. It has an open file option to open a file from disk, and it has a list of your new files. Now, something that we do a little bit differently is that your new files are completely editable by you, the user. So say you don't ever do hollow core panels or you never do panels with legs at your plant, then you can remove these from the list. And that's handled by this directory in my documents that contains all the startup files. So what you can do for this is if you find that you're constantly going in and changing your base concrete strength, you're constantly setting the same analysis options again and again, what you can do is just go in and set all these to have those properties that you find you're setting every time on 95% of jobs. So what we found in our own practice is that typically 95% of our panels are maybe one of 10 types of panels. Maybe a solid panel with legs, maybe an insulated panel, hollow core, for when we do columns, maybe for different material properties. But you can build this out with all of your defaults, so then you're not starting from scratch every time. You're starting with a job that will get you 90% of the way there. And it really saves you time long term if you find you're spending the same time doing the same thing over and over again. So from here, what we'll do is we'll just jump into the new project. And again, we're going to start building out a sandwich panel. But first, I would like to just go over the layout of our interface, go over our design philosophy in this program. Something we really focused on is trying to make this program as intuitive as possible. And what we mean by that is we wanted you to just be able to go in, start designing wall panels. Ideally, you never have to open the help documentation. It's there if you need it, right? And help manual, it's there. Ideally, you never have to go there. We really focused on reducing the learning curve. And part of that meant that what you see here for your input is also your output. That when you do print the report, this just turns into a nice formatted single page. All of these grids kind of collapse down into something that's a little bit more presentable. The buttons disappear, the box boundaries go away. It just ends up in a nice formatted printable page. And that also means you're not getting 40 pages of this mainframe style printout for you to dig through and try to figure out what's important. We really wanted to get away from engineering software doing that. And then another one is how we actually laid out the grouping. We don't have a lot of dialog boxes. I don't think we have any dialog boxes. And then on top of that, we just grouped them into these color-coded tabs. So what you see here in the blue tabs, we have our 4 input tabs: design criteria, concrete extents, structural model, and reinforcement. We have 3 output tabs: analysis results, design summary, and performance summary. And then we have the 3D view, which is really a design aid section, and that's in yellow. So what we'll do now is we'll just start chunking through some input. I'll explain it as we go, what's on each tab, and then we'll start building through that design example. So the first tab we'll start on is the design criteria. The design criteria contains things like your project information, just standard name, client, location, designer, that type of stuff, your material properties, and then in addition to that, we have some specification parameters and analysis options. Now, the load combinations are one thing that's here, and these are fully editable by the user. So you have the option of deleting any you don't want. If you want to run this with a 2, you can go ahead and enter in that value, edit all of these. They're fully editable, add, remove, anything you want. We support the default combinations from ACI 31805 to 318.14, and you get those by just selecting it and pressing load defaults, and I'll set that to the default from that specification. And then in addition to that, we have a set of analysis options, those including stress limits for what your allowable stresses are, your resistance factors, allowable deflections, some multipliers for debonding and development lengths. You have the option of using F'(C) for erection or in place. Or you have the option of using F'(C) for erection or the initial F'(C). You can apply 1.2 mcrack for flexure or not. You have some options for how you want to handle second order effects. You can enter an initial bow, so say you know you have a 1-inch initial bow, you can just go ahead and enter that. And then you can enter percent composites, and as well as the number of elements used in the analysis. This is a point I'd like to touch on a little bit later in, so we'll just be referencing back to the number of elements. The next tab is the concrete extents. So one thing that we really focused on is giving you these graphical aids anytime we could. So all the drawings you see here of concrete are to scale, and they are updated real time. So you can see that this panel is 6 feet wide, and then if we change this to 8 feet, it immediately updates to 8 feet wide. And another thing you may note is that our dimension for length, any length that you see that's input, it's not forcing you to input feet or inches. We instead let the user mix it. So you can do something like 7 feet, 10 inches, and it knows how to interpret that. Alternatively, you can do 8 feet, and it knows exactly what 8 feet means, or you can do 96 for 96 inches, and it can interpret that. So it's really provided this way so you can just input this data exactly as you think about it. You don't think that a panel is 213 inches tall. You think of it as a mixture of feet and inches, so we just let you enter it that way, hopefully reducing your need to pull out a calculator at every step along the way. So what we'll do is we'll build a sandwich panel. We'll leave the 20-foot height, and the 8-foot width. And then right now we're doing a 3-2-3 panel, which sounds good. We'll put 6-inch M blocks. And again, you see that those update real time. And then in addition to that, we have the option for legs, voids for hollow cores, sections, holes, and reveals. So we'll add a hole and a reveal. And we know that this panel is 2 feet from the left, 6 feet from the bottom, and it's a 4x4 opening. And again, all these openings update real time. So you can see that it's dimensioned. And if you accidentally add a typo, it's very easy to do with the amount of input. You'll see immediately that, no, this isn't what my panel looks like. I must have entered something wrong. And that's what I mean by reducing the learning curve. We're not giving you X location, Y location, X length, Y length, like a lot of software does, especially engineering software. It can be very brutal on having to figure out exactly what they mean. We're giving you these to-scale dimensions, so if you enter a number and it doesn't look right, you can see, that 6 is here. I thought I was measuring it from the top, and then you know immediately that's from the bottom. It really does reduce the learning curve, we found. We'll also add a reveal at 11 feet, 11 inches. That is the full width of the panel, is 1 inch tall, and 3/8 of an inch deep. Then we have a hole and a reveal. And something else that is useful when inputting concrete is the use of the 3D view, because this updates real time. So you can see firsthand, just open it up, is this what I expected it to look like? And here you can see that we're using 4-high lifting, so we'll fix that down the road because we intend to use 2-high. And then another thing that you can do is that you can split these views and then have these side by side, so that as you're updating your concrete, if we want to do the same thing before, make this a 6-foot wide opening, you'll see that the 3D model updates in real time, and it gives you a great 3D representation of what you're actually designing. So I'm just going to switch this back to 4 feet. And then from here, we're just going to move on to the structural model. Now, the structural model contains things like loading or strain information, your stripping lift points, all that type of information. So working just top to bottom through this, the first option you have is the bottom connection, if you want it to be a pin connection or a fixed connection. The next one are what we just call panels. By default, you're always designing the panel here that's marked as current, but what you can do is you can add additional panels above. And the advantage of doing that is that instead of having to do all the load tracing yourself and figure out what load is coming in at the top of this panel, you can add 3 panels, 4 panels, as many panels as you want above, input the loads on those panels, and it will automatically add those unfactored loads to the top of this panel. So it just saves you a step of having to do that yourself. The restraints are fully editable. You can have as many restraints as you want. You just enter the position, and then we do have options for spring types of restraints. You just have to enter the stiffness of the spring. We'll also add in a concentrated load. So we'll put it 1 foot below the support at 17 feet. The eccentricity is 0 inches from the inside face. And then we'll just put in some dead load, some live load, and some roof loading. And then you see that our diagrams here are updating. We mark the exterior face. We mark the position of load P1, and then we show you its orientation. So if you have 10 loads on this, it gives you a quick indicator of where you're positioning all your loads, their relative magnitudes, and then from these grids off to the side, you get all their values, all the individual magnitudes. We'll also want to add a wind load that spans the whole height of the panel. So we know that it'll start 0 inches from the bottom of the panel, 0 inches from the top of the panel, and then we want to add 0.1 KLF of pressure and 0.12 KLF of suction. Now these do get added as uniform loads, but if you want them to be trapezoidal, we do give you the option of ending the end magnitudes. In addition to that, we take in soil loading on the external face and the interior face. You enter the external grade and the internal finish floor, and then whatever additional surcharge loading you want to add. You can enter temperature loading. So we'll put in a 30-degree temperature gradient, and this is just added by adding a bow to the panel. So this is just bowing the shape of your panel. And then we'll also put in, we won't put in any additional weights, but the option for putting in additional weights for dead load, or if you have any additional weight that you want to exist through the life of the structure, but not increase any capacities on your structure. So if you're putting like a brick fascia on this and you want to account for the weight of it, but you don't want to just increase your panel thickness because that isn't really concrete and you don't want to be taken account as such. From there we get into stripping and handling. So the first option you see is to use default lift locations. So what that means is that if you're using a 2 or 4 point pick, we're going to automatically place those lifters at these locations to minimize positive and negative moments. Now, one thing, we don't place it at exactly 0.207 times the height. Instead, what we do is we round it to the nearest inch to make it a constructible value. Because what we found is that, yeah, this value may minimize moments, but it's also an irrational number, and they're going to be placing these at whole inches anyways. So all we do is round these values to whole inches. It really just saved us having to edit these numbers on 100% of jobs that we were doing. And again, we'll change this to a 2-point lift, and we'll also change it to a rolling block. You have the option of editing your load modifiers. By default, it's just using what PCI recommends. Handling, we want to just be the same location as lifting. And then for erection, we do want to use an edge lifter, but we just want to remove this lifter at 15 foot 10 inches. So we'll use the bottom line and then our edge lifters for erection. Our next step is the reinforcement input. Now we support 3 types of reinforcement: strand, mild reinforcement, just rebar or mesh. And the first thing you'll see, you have the option of just adding or removing, but you see these auto select buttons on strand and mesh. Now what those do, for strand, it just adds in the minimum amount of pre-stress to meet the minimum pre-stress requirements in ACI. So clicking this button just adds in enough pre-stress to hit that 225 requirement. And it does assume a 15% loss, which can be a little high, but we thought that 15%, well, on our typical wall panels, we really never saw losses exceed 15%. So by assuming a 15% loss, it was just a great initial consumption that we're going to hit that minimum pre-stress requirement. And then for the welded wire reinforcement, what AutoSelect does is it just adds in the minimum amount of mesh for the transverse reinforcement to the design. So following ACI 31814, that's 0.0012 B times H. So we just click that and it automatically adds in the mesh. And we find that typically for our typical pre-stressed wall panel, this is really all we need to do for reinforcement. Minimum strand is really enough to carry our strength requirements, and we're typically okay for this. That's not true all the time, but typically that's true. Sometimes what we do want to do is go in and move these to dodge openings, and you can do that by, if you just select an entry, we give the horizontal position of each strand, so you can adjust these positions horizontally to make them not get cut by any openings you may have in your panel. Now, the next thing that we're doing, that's all the input, so we're just going to run the analysis using this button here. So when we click it, you can see that our bottom status bar changed to analysis started, and this bar does update in real time as the analysis progresses. So on average, it takes about 6 to 8 seconds for a panel. Depending on your panel geometry and what you have going on, it may take a little bit longer, and it does vary computer to computer. One thing that would affect that is the number of elements that you have selected. By default, we support 20, 50, or 100, and we keep that on 20 elements. And I know one concern with using a small number of elements is that you may miss a point of concern, like maybe your controlling flexure section isn't at 20th points, so 20 elements wouldn't give you that location. But that's something our program kind of handles a little bit more intelligently, is that when you pick 20 elements, that's really a minimum number of elements. And if you have anything happening between 20th points, it's going to add an additional point. So if you have a point load coming in between 20th points, or concrete extents changing, or reinforcement stopping or ending, we're going to add an additional point. So it's really just, like I said, a minimum number. Typically, we may be running it with 20, but you'll see 27, 30, 35, somewhere in that range. And then we'll run it with 20, and then just when we go to submit our deliverables, we'll kick it up to 100. You run it, you get smoother looking curves. It just makes it look a little bit nicer. Another thing you see is we have 2 flags on the bottom. The bottom one just tells you what your analysis status is. So any change that you make, well, then this will change to out of date. It will turn red with an X, and then it will just tell you that you need to run the analysis again. And then in the bottom right, we have the design status, and that just tells you for this current run how to do. How are you passing? Are you passing all your requirements? So the green check just means that we're passing all of our requirements. If there were ever to be a failure, it would become a red X, and this whole thing would just turn red. So now we're just going to jump through the output. For the output, we're going to kind of work in reverse order. The final 2 tabs are what we typically use as our deliverables, the design summary and the performance summary. So we'll start with the performance summary. The performance summary is just a dashboard for your panel's performance. It's really exactly that. It's how does the panel perform from when it's cast to when it is in place, or when it's stripped to when it's in place. So what you'll see is you have your project information on top, including the location, designer, project name, that type of information. And then we'll give a list of all the panel properties, including concrete strength, what your maximum allowable deflections are, your maximum allowable stresses. It will give what your initial losses are and your final losses, what minimum pre-stress you got. And then as well, we'll give you what deflections you have and your deflection limits. And then after that, we have 4 different stages. We have the stripping, handling, erection, and in place. And then for each stage, we give what we define as the utilization, where the utilization is just the demand divided by the capacity. So we're really looking for numbers less than or equal to 1. Any number greater than 1 implies that we are overutilizing this and that we don't have enough capacity to meet the demand. So for stripping, we give the maximum loads on the inserts. We give the shear utilization, the flexure utilization, and then your maximum compression stress, your maximum tension stress, and that's everything you need to know for stripping. If any of these numbers were to exceed allowable values, they would turn red, and then this would have also been red in the corner. So you immediately know if you have an error. But by quick glance, we can see that we're not utilizing this panel very much. Our largest utilization is flexure for in place, and that's only 30% utilized. So for handling, we give the same information. For erection, we give the same, but we also give you the loading on those edge inserts. And then for in place, we give the same information, but then we also give what the controlling load combinations are, just so you know what cases are giving you this controlling flexure and shears. And then for this flexure combination, we also provide the interaction diagram for that, showing you your PM diagram, your PPN, the maximum amount of tension you can put on this panel, and then how you currently load it. And then we also give all the loading, and this is just a table printout of all the grids in this view for all of your loading. And what this is used for, we say what P1, W1, W2 are, because down below we give another diagram of all your loads. just so you have a printout of all the loads that are being applied to this panel. And then we give 3 graphs down below. The left one is flexure utilization, and then we have the compressive stress and the tension stress. Now, what these graphs are moving up the memory. We're just plotting the maximum flexure utilization, and then as well as the maximum compression and tension, and then we color code them based on the allowable limits. So you can see if you ever have any red, if you were ever to have any red in this graph, that means you're above the allowable limit. So here, if this big spike in the compression stress at the opening were to turn red, you would know that at your opening, you've exceeded your compression limit. And by having no tension, you see that this graph is just completely empty. This panel has no tension in it. Another thing you can do, we plot these by default to make them as large as possible just so you can kind of see the variations. But if you wanted to see the limits, you can check show limits, and then it just draws a line at its relative limit. So here we draw a line at 1.0. You can see we're not really utilizing this. Again, we have no tension. And then for compression, you can see we're about halfway to the allowable compression limit. And another option is for stresses, you can have your tensions be scaled on the same axis as your compression to get you a better feel of how your tensile stresses compare to your compression stresses. The next tab for our output is the design summary. Now, our design summary is, again, it's the second half of what our typical deliverables are. And this is just well, it's automatically created and we use it. Our engineers use it, that they print this and then hand it to our CAD tech so that the CAD tech can then sketch up the panel. So what we provide is we provide, again, all the project information. We provide the typical section, what reinforcement is in the typical section. We provide the concrete mix information, the primary top and bottom reinforcement, the live load and total deflections, as well as the stripping and blocking detailing, and then some information for how you want to strip, erect, and then revision and design number. Now, all these numbers, or these values with boxes, are editable by the user. So you could go in and define how you want to strip it, how you want to erect it, the revision, the design number. You can give your concrete mix a name. You can define who the checker is, and you can also set your company logo here in the corner if you have one and you want to be included in the drawings. And again, this is something that we had to make on every single wall panel that we designed, and it was taking us about 30 minutes on average. So, and that's not including revisions. Every revision means another 30 minutes going in and remaking the sheet. So this saves us 30 minutes a panel just by this being automatically created. This is a huge time saver, at least in our operation it's been. I think it'll be in yours too. The third tab for our output is the full analysis results. Now this is the full-fledged report. We don't often give this for our deliverables, but it does provide in full detail everything that's going on in this panel. So the first thing you'll see, and we'll just work through this top to bottom, kind of jumping over some repeat data. But top to bottom, you'll see our shear and our moment envelopes, as well as the values and the locations of any maximum and minimum. We give a list of all the load combinations that we're checking. We give additional top end forces. So what this is if you have a stack of panels on top of this, it will give you what those unfactored loads are that are bearing down on top of your panel. And then it also gives your loads at all your restraints on your panel. Down below, we draw the panel on its side, and we show you the location of your controlling shear section and your controlling flexure section, and then show them graphically by putting a dashed line through it and then marking them V and N for shear or moment. And then if one were to fail, these would also turn red as well, just to give you a quick indicator that your flexure may be failing at 120 inches. Now what we're going to do is we're just going to strip through the stripping section of the printout. So for stripping, what we give for stripping is we give a few graphs and then a few what we call section views. So our graphs are, we give a shear and flexure utilization. So in the blue curve, as you hover over it, it shows you the data. And it also, the data is, the X is the location and the Y is your shear utilization. And similarly, the black curve is our flexure. So you can see any data curve or any data point on the curve, which we think is a huge benefit because curves without knowing the data isn't really that useful. And we also give the maximum shear utilization and the maximum flexure utilization, and as well as their location. And then similarly, we give a stress curve showing the top stress in black, the bottom stress in blue, and then the compression limit and the tension limit. And we show you the maximum and minimum stress. And then we give two more curves for shear and for flexure. And for those curves, the black line is the demand, and then the blue line is the capacity. And then we also give your maximum and minimum locations, and any zero shear or zero moment locations that you have. And if at any point in any of these curves, your stresses, shears, or moments exceeds the allowables, that will also get flagged in red, just giving you a big indicator that you're over your allowable limit here. Then we give your loads on all your inserts, your center of lift, your tilt potential, and then we give what we define as a section view. Now, I know our idea behind the section view is that we wanted to give you everything we knew about that section so that you can kind of see what's going on behind the scenes. Just giving you what your flexure capacity is great, but we wanted you to be able to trust the program, do some quick hand calcs. Maybe you're a little bit over, but you can then pluck out what we know about the panel, your losses, your area of steel, where your neutral axis is located, the orientation of your neutral axis, your cross-sectional area. We give you everything here to make the program not a black box, so that if you ever want to go in and verify any of these numbers, we give you all these values that you're capable of doing so. And we really think that's a great thing for a user to have, because I know that using a new piece of software, I hate just being told a number and told to trust it, because you don't trust it. It's your first time in the program. You want to be able to verify some of these numbers. And a lot of the times, if you go in here and your capacity looks a little low, but you don't know why, maybe AS is 0. So maybe it'll just shed some light on what's going on. And then in addition to that, we show you the section that we're performing this calculation on. So if you have any reveals or openings, they would show up here. We show you which phase is your compression phase, and we show you all the reinforcement. And as well, we show, again, the location of that flexure section. And then similarly, we show the same thing for shear. The controlling shear section happened to be at the opening for stripping. And it sheds a lot of light on what's going on. The next stop is our service summary. So one thing I'd like to point out is our document navigation. So at any point, you can click on one of these sections to jump to the section. And if you don't want to see the section, you can uncheck it, and it hides it from the report. So it allows you to fully modify what you see and what you print if you wanted to print this full printout. For our service summary, we give a plot of your maximum and minimum inside face stresses, your maximum and minimum outside face stresses, and your max and min deflections. And again, if at any time it exceeds the allowables, those will be immediately flagged red. Our final section is our strength summary. We didn't want to show you all 11 load combinations of strength just because that's a little verbose, and we decided that it'd be more benefit to you only to print out the controlling cases. So here we provide one plot for utilizations. Black again is flexure, but if you hover over it, it gives you the location, how much is utilized, the demand, the capacity, and the load combination that provided it. And similarly, it does the same thing for shear. We also give the shear envelope with max and min shears, a moment envelope with your maximum and minimum moments, and then we give two more section views, one for flexure and one for shear. Now these contain the same information, but they're oriented differently now, with your exterior face on top and your interior face on bottom, where before it was just top inform and bottom inform. We still show the compression face, but in addition to that, we give you the PM diagram as well. And then from there, that's all the printout that we have. If you want more information, you can view any load combination. But from there, typically, we would then just print our final two. We would print just the design summary and the performance summary once we're satisfied. And again, that's a deliverable. It's short, it's concise, very easy to understand, just a 2-page printout. And that ends up being our deliverable. So one more thing before we wrap this up that I'd like to point out is our quality control document, which you can get to by going to Help QC Document, because what our QC document is a document that contains 6 fully worked out hand calculations. And for each hand calculation, we give our software's values, the hand calculation values, and a % difference. So for any of these numbers, you can go in, and if you want to know how we calculate it, you can just go to the MathCAD section, and then you can see the fully worked out calculations on how we get these numbers. And it does shed some light on how we do things, and it really just answers, we find, a lot of our users' questions. And another thing that makes us different is our technical support, that if you ever email or call us, all of our software developers on this also are structural engineers. We all have master's degrees in structural engineering. So if you call us, get on the phone, or email us, we all have a very good insight into what the program's doing, but we also understand the code. We understand engineering theory, we understand ACI, so we can kind of help you on both ends of things. And that's everything for this webinar. I'd like to thank you for joining us today. And if you have any questions, we'll leave this line open so you can ask questions. We'll be on the line for a little bit. Again, thank you again.